We would now like to apply the Biot-Savart to a variety of different current-carrying wires and calculate the magnetic field associated with them. Let's recall that the Biot-Savart law, in its abstract form, says that the magnetic field at a field point is equal to the integral of mu naught over 4 pi, the integral over the source of the current element, I ds, cross a unit vector from the source element to the field point, divided by the distance dsp to the field point squared. And you'll notice that in this law, there's a lot of similarities to our Coulomb law for continuous charge distributions. We have the cross product. We have a different source element. Now, let's consider a portion of a wire. So we'll draw a picture like this. We'll have a wire with a current I. And now let's just take this wire to be of length L. And let's imagine that somewhere the wire has some type of power supply that's producing the current that goes around it. And I just want to consider the effect of this straight part of the wire at some field point P, which I'll draw over here. And I want to know what is the B field at this field point. Well, what's important to begin the analysis is to choose a good coordinate system. So the way I'll do that is I'll draw my wire. I'll pick some type of origin, and I'll pick it coordinate system at the center of the wire. I'll have unit vectors I hat, j hat, and I'll choose a right-handed system k hat with k hat in that as direction shown. And I'll put my field point P right here, and I'll give it coordinates x and y. And now this is my finite wire. And what I want to do is pick a source element in this wire here. I'll exaggerate its size. And this is my I ds. And now the crucial thing is to, in this coordinate system, to choose a integration variable. So I'm going to call this my x prime. And I want to draw the distance. That's our r ds to the field point, and that unit vector points out. And this is enough. We just still have to relate the length of our source to our integration variable, so we have a dx prime. Now, there's still one thing to keep in mind, that we have a unit vector here, and when we do the integral, we're going to be adding up a lot of pieces, and you can see both the direction and the distance to the field point will depend on which source element we are. And in order to express these two quantities in our coordinate system, we can do the following thing. Let's draw a vector r prime, vector r, and the key vector that we want, r minus r prime, the length of that vector, r minus r prime, is precisely equal to the r from our source element to the field point, and the unit vector that we want from the source vector to the field point is r minus r prime over the magnitude. Now, these two vectors are easy to see. The vector r is to the field point, so we write it in Cartesian coordinates. And the vector r prime is to the infinitesimal current source, and that's equal to x prime I hat. And so it's a trivial matter, well, not trivial, but it's just vector subtraction to write this unit vector as x minus x prime I hat plus y j hat. That represents r minus r prime, and we use the Pythagorean theorem to get its length, y squared to the 1/2. Now, you could have done all of this just with Pythagorean theorem and vector decomposition. This is another nice way to do it. And so now we can write down the magnetic field. And now I'm introducing very explicitly the field coordinates, x and y. This is in the plane. It's equal to the integral. Well, our integration variable is going from minus L to x prime equals L over 2. And so the limits over this small section of the wire is given by that. And now we have the constant mu naught over 4 pi. We have I dx prime I hat cross the r hat, which is x minus x prime I hat plus y j hat. And downstairs, we have 3 to the 3/2 power because there's a squared there. So this is x minus x prime squared plus y squared to the 3/2. Now, one of the things that we see immediately is that we don't have to, when we take this cross product in our coordinate system, I hat cross j hat is k hat. And of course, I hat cross I hat is 0. And so the only piece that comes in here is the I hat cross j hat. And so we get this is equal to x prime equals minus L over 2. A little tedious to write this out. Mu naught I over 4 pi dx prime over x minus x prime squared plus y squared to the 3/2. Now remember, the integration variable, this is in the k hat direction. I haven't forgotten my y yet. But the integration variable is x prime. So the y is not being integrated over. And so you see we have a few constants. Now, this integral is equal to, so we need an integration formula. And our integration formula I'll put over here, dx prime over x minus x prime squared plus y squared 3/2. This is equal to minus x minus x prime over x minus x prime squared plus y squared to the 1/2. And I have to divide by 1 over y squared. You can try this yourself by differentiating this quantity. And so what we get is minus mu naught I over 4 pi. Now notice there's a y up here and a y squared downstairs, so I have a y down there. And I have in here x minus L over 2 over the denominator, which is x minus L over 2 squared plus y squared. We're running out of room. To the 1/2 minus, this minus sign is out there. So it's x minus L over 2. So that's plus L over 2 over x plus L over 2 squared plus y squared to 3/2 to the 1/2. And there we have it. Now, this is a mess, but you can see what's a very nice exercise to do is to look at bxy in the limit as this little length of the wire goes to infinity. So we're talking about a very long wire. Now, I'm going to do this by pointing out these terms. When we look at this limit, L goes to infinity, L is much, much bigger than x. So in the numerator here, we can ignore the x. We can ignore the x here. And so we just have minus L over 2 minus another L over 2. And that's going to give a plus sign on the outside with an L. In the denominator, we can ignore the x. We can ignore the y too. We're assuming it's much bigger than x and y. And the denominator is just L over 2 squared to the square root. So that brings a factor 2 upstairs. And in this limit of our big result, what we get, by the way, I didn't include that this is pointing in the k hat direction. The limit becomes the 2's come upstairs, cancel that. The minus sign comes out. The L upstairs cancels the L downstairs. And we get this nice, very simple result, mu naught I over 2 pi y in the k hat direction. And that's the field. This expression, we have to be a little bit careful because we calculated it in the positive plane. This is for y bigger than 0. But if y is less than 0, it also holds, because then the direction would be negative k hat, and that's downstairs. So in fact, our result is good. Whether it's above or below the plane, what we have to be careful about here is y is not equal to 0. So there's the magnetic field of a wire that's both finite in length and also the limit as the length of the wire goes to infinity using the Biot-Savart law.